Okay, let's start. Today I will talk about decision trees. Tree structures, impurity, and recursive function will be important in this topic. So I would like to talk about this topic. Again, continuing from last time, what we want to do is classification problems. We want to classify data. Now, let us think about how we do this by remembering how plants are classified. First, there is a yes or no question about whether they make seeds. Uh, okay. For example, if they make seeds, there is another yes or no question about whether the seeds are inside ovule. When they are not covered, they are called gymnosperms. And when they are covered, they are classified as monocots or dicots, depending on whether they have one cotyledon or not. The idea of decision tree is based on this concept. Decision tree is when we want to classify data step by step and finally predict the level. Now, for example, when we apply this to iris dataset, it looks like this. This dataset is uh, this dataset is made up of 150 samples in total, with 50 samples collected from three types of iris. Each sample has four features, which are sepal length, sepal wise, petal length, and petal wise, like that. Like that. So sepal length, sepal wise, sepal length, petal length, petal wise. And labels are attached to them. For this dataset, when the second feature is less than 2.46 for 5 uh, centimeters, it is classified as class 0, which is setosa. If not, it moves on to the next classification. So what is good about this is that, as so earlier, humans can easily understand and interpret the result. And we can also somewhat understand the importance of features. In this case, the tree first branches based on the second feature. So we can see that the second feature seems important. We can also see which features are used later on in the tree. Although we are thinking about classification problems now, decision trees can also be used for regression, which is related to linear regression that so third lecture. when levels take continuous numeric values. However, in this lecture, we will only deal with decision tree for classification problems. Okay, now let me talk about the tree in decision tree. A tree, also called a tree structure. Uh, uh, it is a type of data structure. It contains vertices and directed edges connecting them. The direct edges are called branch. And when vertex A and vertex B are connected by edge from A to B, A is A is called the parent of B, and B is called the child of A. In other words, this arrow is called a branch. This is easier to understand when this is easier to understand when see from the opposite side. If we draw the tree structure like that, like that. If we draw the tree structure upside down, we have this kind of structure. The arrows from before are pointing in the opposite direction, but the idea is that this structure looks like a tree. A vertex without a parent is called root. In a tree structure, you can reach any vertex by starting from the root and going from parent to child and to child's child. And there is exactly one such path. A vertex without vertex without a child is called a leaf here. So these edges are the edge parts of tree. In other words, leaves vertices at the lower ends of the tree structure. A vertex with children, meaning a vertex that is not a leaf, is called internal node, like that here. Like this vertex here. The number of edges from vertex to the root is called the depth. In this case, 1, 2, 3, so the depth is 3. In the figure we saw earlier, the green circles are vertices, and the arrows edges. The vertex labeled does it pros, does it produce seeds is the root. So this is root. Sorry, root. And these green circles are leaves. The vertex is labeled dicotyledon and monocotyledon, dicotyledon and monocotyledon. Children of the vertices labeled the cotyledons single leaf. This means that the vertex labeled as a cotyledons is the parent of the vertex labeled dicotyledon and monocotyledon. In this case, there are three edges from monocotyledon to does it produce seeds. So the depth is 3. This is the deepest vertex, so maximum depth is 3. Tree structures are used for things other than decision trees. The directory structure for organizing and managing file is also a tree structure. For example, if we think of folders inside a large memory, and more folders inside those folders, that is also a tree structure. Not only that, tree structure are used not just for file management methods, but also for sorting methods called heap sort. They are also used for syntax analysis, which is interpreting sentences. Let us think about how to handle trees in Python. A tree consists of vertices and directed edges. For example, there was a vertex labeled as a cotyledon single leaf, and it has a left child vertex labeled dicotyledon, and right child vertex labeled monocotyledon. We want to handle this as one unit. When we have multiple pieces of data like this, the concept of classes is useful. A class is a way to bundle multiple variable and related operations functions together. To explain it correctly would require a whole lecture, so let me explain it briefly. For example, if you want to handle information about the person's name and age together, you define a class like this. So class person define initialize self name age. So self dot name is the name and self dot age is age. So this init is short for initialize. This is in a way becoming a new type. Until now, we have worked with integers, floating point numbers, and string types, but this is like creating your one type. To show how it is used, by setting and initializing the person object as person one is person name is Alice, comma, age is 30. We create a class called person one that can handle name and age together as one unit. This initialize in init is called when this person object is created and self refers to the object itself. So when person one is person name is Alice, comma, age is 30, is executed. Alice is stored in person one's name, and 30 is stored in person one's age. You might wonder how to see what is inside person one, which contains name and such. You can see the contents by writing person one dot name. I will define a vertex of decision tree using a class as follows. So they have information which features thresholds for splitting the left child, the right child, and predicted level. Uh, this known is a built-in constant that represents the absence of a value. How it is used is like this. Life leaf node 1 is value equals bryophytes, which creates a node and that only has the predicted level bryophytes. We create a tree node with value equals vascular bundle. Sorry, so we create a tree node with value equals pteridophytes for leaf node 2. Then with leaf node 1 labeled bryophytes and leaf node 2 labeled pteridophytes, we create internal node 3 with a value of does it have vascular bundles? With leaf node 2 as left child here. And the leaf node 1 as a right child. So this becomes internal node 3. By executing, we can create a vertex labeled as it vascular bundle, and its child vertices labeled pteridophytes and vascular. This corresponds to the right part of the plant classification image we saw earlier. So this is leaf node. This is leaf node 1. This is leaf node 2. This is internal node 3. So internal node 3 is parent of so leaf node 1 and leaf node 2. With this, I have explained how to write a tree structure in Python. Now, let us talk about how to build a decision tree. Of course, we keep dividing the data, so first we split the data. We want the groups created by splitting to consist of data with mostly the same label. Then we further split the divided data, continuing to split so that the data consists of mostly the same levels. We stop splitting when any of the uh, following conditions are met. When we have managed to make the group created by splitting consist of data with the same labels. When the number of data points in the group created by splitting is too small, when the depth of the group created by splitting reaches a predefined value, the reason for this limitation is that if we split until each group contains only one data point, we can perfectly distinguish labels for the training data. But this will certainly cause overfitting. So the predictions on text data will likely not go well. Therefore, specifying a minimal number of samples for splitting or a maximal depth is a commonly used technique. Random forest and boosting are also sometimes used to avoid such overfitting, but we will not go into detail about them today. Earlier I mentioned data consisting of roughly the same levels, but the question is how to express this. Let's say there are NI data, NI data points with level I in the data. We set pi is NI over N. Then to check whether the data consists of roughly the same levels, there is a metric called impurity. And this is not just one type, but includes that I will introduce here as Gini impurity, Gini impurity and entropy. The Gini coefficient is called calculate as follows. Entropy comes from the concept of information content and is calculated as follows. Let's focus on the Gini coefficient here. For example, if we examine 10 data points and 6 have level 0 and 4 have level 1, the Gini coefficient from the definition G1 is 1 minus, so level 0 is 10 over 6, and level 1 is correspond to 10 over 4 over 10. So by the definition, G1 is 1 minus 6 over 10 square minus 4 over 10 square. It is equal to 12 over 55. On the other hand, if all 10 data points have level 0, then G2 is 1 minus 1 square, it's equal to 0. So when data consists of only the same labels, the Gini coefficient becomes zero. And the more mixed labels are, the larger the Gini coefficient becomes. Indeed, there are earlier case where 6 data points have the level 0 and 4 have level 1 gave us 12 over 55, which is greater than 0. So you can see that this seems to be indicator of whether the data consists of the same levels. Entropy also has similar property. In the case of entropy, when all data has the same level, Pi becomes 1, then since log to 1 is 0, the entropy becomes 0. Uh, the implementation of Gini coefficient can be calculated using binary count, which was introduced in the K-nearest neighbors lecture. Here, Y is the array of levels, and we get n by counting the number of data points. When the data is empty, division is not possible, so we decide to return 0. Then we count the occurrences of each level in Y and calculate the probability of each level. Since counts represent the number of occurrences of each level, dividing this by the number of data points n gives us the pi we calculated earlier. Now, when we squared one-dimensional array, each element is squared, so probes squared it represents the squared probability pi squared arranged in an array. Subtracting the sum of these from 1 gives us the Gini coefficient. The decision tree ultimately looks like this, and when splitting, we calculate so that this Gini coefficient would be small as possible after each split. Let me explain specifically how to do this. We have some data. Let's look at just the case features and say we will divide the data based on whether the case filter is less than or greater than threshold A. Let's call the set dataset where the case filter is less than or equal to the threshold A as the set L. And the set where case filter is greater than the threshold A as set R. Let's call the impurity of L as IL and the impurity of R as IR. And the number of the data points as NL and NR respectively. Since the number of data points is different in L and R, we take a weighted average of their impurity. If the both impurity is 0, then this will be also 0. So we choose the threshold A and the future K so that this value become as small as possible. So the algorithm look like this. For each K future, future, we perform the following process. Sort the data in ascending order of case future. For each j, consider the set L consisting of the first two j's elements and the set R consisting of the j plus 1s to nth element. Calculate the impurity and perform the weighted calculation from the previous page. Here, find the combination of j and k and minimize the ikj. And split on the case future using the threshold. At this time, the threshold we use in between xijk and xij plus 1k. That is, xijk is at the edge of L, and xij plus 1k is at the edge of R. So if we split by taking the average of these, we know that the impurity will be minimized. Let me try to make this clear with an actual example. Let's say we have data like this. So, two, three, four. So, x1 is 0, 0. Levels is 0. X2 is 2, 0. This level is 0. So x3 is 1, 1. So this level is 1. Finally, x4 is 3, 1. This level is 1. So the first two data points have level 0, and the remaining data points have level 1. First, let's sort by the first feature in ascending order. The order is, so in this case, we look at here. So in ascending order, the order is 0, 1, 2, 3. So data points are arranged as x1, x3, x2, x4. So x1, x3, x2, x4. Now let's look at the impurity. Here we consider Gini impurity. When we calculate the impurity of the first data point x1 and the rest, for just the first data point x1, of course, the Gini coefficient is 0 because there is only one data point. For the rest, the probability of level 0 is 1 over 3, and the probability of level 1 is 2 over 3. So the gene coefficient is 1 minus 1 over 3 square minus 2 over 3 square. So 1 minus 1 over 9 minus 4 over 9. So it's 9 over 4 over 9. When we calculate the weighted average, the first part is 1 over 4 and of the data, and the second part is 3 over 4 of the data. So I11 is 1 over 3. Next, when we check the impurity x1 and x3 together, there is one each of level 0 and level 1. So gene coefficient is 1 half. Similarly, in the other side with x2 and x4 also has one each of level 0 and level 1, so gene coefficient is also 1 half. So I12 is 1 half. Similarly, I13 is 1 over 3. Therefore, for the first filter, I11 and I13 are both 1 over 3. But let's choose I11 here. For the first filter, the threshold is between 0 and 1. So Gini coefficient is minimized when the threshold is the average of 0 and 1, which is 1 over 2. In other words, only x1 has the first filter less than or equal to 1 half, and x3, x2, x4 have the first filter greater than 1 over 2. Their impurity 0 and for 9 over 9 respectively. Next, when we sort by the second filter in the ascending order, the order remains the same x1, x1, x2, x3, x4. Sorry, x1, x2, x3, x4. When we calculate the gene coefficient for the second filter in the same way, the first part is x1, x2 only has level 0. And the other part, x3, x4 only has level 1. So both gene coefficients are 0. So the weighted average is also 0. Therefore, for the second filter, the gene coefficient minimized when the threshold is between 0 and 1, which is 1 half. Comparing 1 over 3 and 0, 0 is smaller. So we know that it's the best to split based on the second filter with threshold 1 over 2. Okay. Now it takes 14 minutes, so let's take a break. Okay. Okay, let's restart. The well, since we have encountered the concept of minimal value, let's also confirm the algorithm to find it. When we have a sequence, uh-oh, uh, How do we find the minimum value in that sequence? Actually, this can also be written as a program. We first test set a variable m to a large number. For each number, if we encounter a number smaller than m, we replace m with that number. If we repeat this process, in the end, m will be the minimum value of the sequence. The problem looks like this. The values here is the sequence, and we use for loop to get each element from it. If value is smaller than mean value, we update mean value to value, which gives us an algorithm to find the minimum value. So, summarizing what we have discussed so far, the method of data splitting in decision trees is also a matter of finding the minimum value. Therefore, we first prepare a candidate for the minimum value and a variable to store the minimum value and then loop through for the futures. We sort by the case future and calculate in the impurity. Calculate the impurity. No, here. For when each point is chosen as split point. We set L as label up to JS element and R as label from the JS element onwards. Calculate the gene coefficient for each and compute the impurity. When this impurity is smaller than impurity we have encountered so far, we update this best I with I. At that time, we also store information such as thresholds that realized this and which filter we split on. So we have now completed the data splitting part mentioned at the beginning of decision tree construction. The way to build a decision tree is to repeatedly split the data to minimize impurity as much as possible. We do this splitting even for all the already split data, further dividing it to increase purity. When creating a decision tree, it is useful to have a way to repeat the same process over and over. And that's where recursive functions come in. Yeah. When creating a decision tree, we need to further split the already divided data. There may be cases where we want to use the same function inside a function, and that's when the recursive function can be used. Recursive function is a function that performs processing by calling itself. and it consists of two parts. These two parts. The first is a base case. This determines when to stop. Since the function calls itself, if you don't set this property, it will never end. This is a termination condition. The second is a recursive case. This is where the function calls itself and processes by dividing the problem into a small subproblem. A famous example of using recursive function is a function to calculate for factorials. Let's consider a function called factorial n. When n is 0, it returns 1 on end. When n is not 0, it calculates n times factorial n minus 1. What happens in when we calculate factorial 0, since n is 0, it returns 1. When we calculate factorial 1, since 1 is not 0, we go to recursive case and calculate 1 times factorial 0. We have already know that factorial 0 is 1. So 1 times 1 returns 1. What happened if we input factorial 2? For 2, we calculate 2 times factorial 1 to find the value of factorial 1. So we need to calculate 1 times factorial 0. And since factorial 0 is 1, factorial 1 becomes 1 times 1, making factorial 2 equal to 2 times 1. This creates a structure where we keep going deeper and deeper into the function. The algorithm for building a decision tree looks like this. First, for when to end, we terminate as a base case under the following condition. When the number of data points become too small, when the depth of the vertex being considered reaches the maximum depth, when the data contains only one type of label. When any of these conditions are met, we return a leaf with the most frequent label value, the labels that appear most often as a predict label. In the recursive case, we repeat the process as follows. Split the data to minimize impurity. Let the collection of data smaller than the threshold be L, and the collection larger than the threshold be R. Recursively apply the decision tree creation algorithm with L as the training data and D plus 1 as vertex depth to obtain vertex TL. Similarly, apply the algorithm with R as training data and D plus 1 as vertex depth to the obtain vertex TR. Return vertex with vertices TL and TR as its children. Since decision tree can be represented using a tree node, cross as shown, the implementation looks like this. Well, the first part is the best case. When the data count is small, here. So when the data count is small, the maximum depth is reached, or there is only one type of label, a tree node with leaf value, as its values is returned. Next, we find the best split. And if all the data cannot be properly split, such as when all the explanatory variable data is same, we process it as leaf. If we can split, if we find the well, if we can split the data properly, we recursively construct the left and right child nodes and return tree node that has its left and right child. Through it might seem strange to these seeing it for the first time, this successfully creates a addition tree. What we get is a structure like the Aris data example. For instance, if the second phasor is less than or equal to 2.45, it's class 0. And if not, we need to further splitting because it's not well separated yet. So we split based on the third filter at 1.75, which minimizes the gene for coefficient. How to predict labels with decision tree can be written as follows. This code is also a recursive function. First, when looking at the content of tree, if there is something in the value, we return it. If not, we determine whether the further value is less than or equal to the threshold, and if less, we look at the left node. And if it's greater, we look at the right node. By constructing such a recursive function, we can also predict labels with decision trees. By the way, if you use a machine learning library called scikit-learn, you can write this quite concisely. The decision tree obtained with scikit-learn looks like this. In this figure, when the petal length is less than or equal to 2.45 centimeter, it goes this way, and the gene coefficient becomes 0. If not, it shows how to classify based on the size of the petal width, making it easy to read. We will cover scikit-learn in more detail next time, so let's just introduce how it can be used here. To summarize the characteristic of decision tree, the advantages are the results are easy for a human to interpret. For the future importance is clear. They don't depend on distance between features. In the previous Kenya's neighbor method, we depended on distance between features. But in the case of addition trees, we only check whether the number is larger than or smaller than a threshold. So it doesn't depend on distance to other features. We used them for classification problem this time, but they can also be used for regression. That is when y takes continuous numeric values. On the other hand, disadvantages are when the tree depth becomes deeper, it's prone to overfitting. When there is a large imbalance in the number of data points per class, the Gini coefficient will remain large no matter how we divide the data, making accurate prediction difficult. While they can be applied to nonlinear problem, they are not good at the linear separable data like that because they split based on feature at a time, even in situations when data could be separated diagonally, so like this. Since they are split by feature, linear classification actually doesn't work so well. Results can change greatly with small change in data. Just adding or removing one data point can change the result. Predictive performance may be somewhat inferior compared to other methods. Therefore, to improve predictive performance, there are methods like bagging and random forests that use multiple decision trees. The idea of random forest is that if there is variability, let's create many decision trees and use their average result. Regarding decision boundary, when we accurate or plot them, they look like this. The data itself is simple enough to separate it by some straight lines, but because decision tree is split by each feature, the decision boundary looks like this. As for how to determine the depth, we can use cross-validation. And when we examine the depth using cross-validation, it looks like this. Showing the depth 3 or 3 is appropriate. However, even at the best, there is still an error rate of about 6%. Whether we consider this small or not, it's a relatively large error rate. Okay, now let's explain the code for addition tree. But let's take a break. Okay, let's restart. Some installation are needed. So let's start with preparation, execute. The pip install command is used to install things that are not included as standard. This time we will install some useful library for drawing graphs. Okay. This will take some time to download, so in the meantime, let's check the function to find the minimal value. In class, we discussed how to write a function to find the minimum value from a list. To find the minimum value, we set an initial value and then look for the minimum value from the value array. We look at each element one by one. For each element, its value is smaller than the current mean value. We update it. By doing this for all data, we keep updating the minimum value candidate when we encounter a smaller number, so it keeps getting smaller. So by checking all data, we can obtain the minimum value. This is how we actually use it. When this code is executed, the mean value in the list -2 is displayed. Let's take a look at another technique just for what comes next. Let's try a function that finds the minimum value while skipping specific conditions. For example, let's say we want to ignore negative values and find the minimum among numbers greater than or equal to 0. In such cases, we can use what's called the continuous statement. Through the initial setting of the minimum value is the same. So this is comment, remove. If you try it Python with Python tutor, let's try. Sure. And so read comment. And so there is no NumPy, so we change here. So large value. So very large number. Okay. Okay. Oh, I forgot it. Okay, Visual Execute. Okay. Hmm. Okay. Well, first the data array contain this list. Mean value is set to large number. When entering the for loop, first value is 3. Since 3 is not less than 0, it enters the comparison, and since 3 is less than mean value is updated to 3. The next value, 2, is also greater than or equal to 0. So it enters a comparison, and since 2 is less than 3, main value is updating to 2. This repeated. So this repeats until reaching -2. Yes. Okay, since -2 is less than 0, continue is executed. And the sequence statement are not executed, returning to beginning of the loop. This is how the continue statement works. So like that. After that, when 1 comes, since 1 is greater than or equal to 0, 2. So since 1 is less than 2, mean value is updated to 0, 1. In this way, by using continue, you can skip elements that don't meet certain conditions. Now let's move on to recursive functions. Recursive functions, as I explained earlier, contain a base case and recursive case. If we check with Python tutor, edit code. Okay. When 4 is our input, it calculates 4 times, so 4 times factorial 3. So here, so 4 times 4 factorial 3. Factorial 3 is called, and it calculates 3 times factorial 2. Factorial 2 is also called as function, and 2 times factorial 1 is calculated. Factorial 1 is factorial 1 is 1 times factorial 0. So factorial 0 is called again here. Yes. Then, so 1 is returned here. So factorial 0 returns 1. Therefore, the result of factorial 0 is determined to be 1. Then factorial 1 is 1 times 1, which is equals to 1. Factorial 2 is 2 times 1, which equals 2. Factorial 3 is 3 times 2, which is equals 6. And finally, factorial 4 is 4 times 6, which equals 24. It's completed, isn't it? So it's famous, complicated, but I hope you understand that this is how it works. I will just focus on helping you understand the basics. Next, next is classes. Basic concept in object-oriented programming, classes are used to group various things together. We have seen integer type, floating point type, and so on, but classes allow you to create such types yourself. Let's create a class called person here. Here. We define it with class person, and within it, we set age and name using a method called init, so initialize. For example, right? Oh, yeah, so if there is a class called person and something like person1 equal person name Alice age is 30 is called an instance of person is created containing a set with the number 30 and the name Alice. If we do person 2 name Alice, person 2 if we do person 2 is person name is Bob, age is 25. Something contains Bob and 25 is created. Inside person 1 is information about 30-year-old named Alice. And inside person 2 is information about 25-year-old named Bob. When you want to access the content, you can retrieve them by writing the object name, so object name, age, or name, followed by a dot and the attribute name, like person1 dot name. So let's execute the person1 dot name part becomes Alice, and person1 dot age part becomes 30. This is what a class is. Think of it as a way to handle data together. Okay. Hmm. Now let's take a closer look at how to implement decision tree. Uh, Decision trees are defined as I explained earlier in the slides, but in code it looks like this. So it's long. This is a class that holds which feather to split on, which threshold to use for splitting, which child node it has, and what the predict level is. For the plant classification tree that appeared in the lecture, it can be written like this. First, we define the leaf node, then define the internal node, and finally create the root node. When you want to see the content of a class, you use a dot, like that. Just like in regular object-oriented programming, for example, if you want to see the value of root, you can see it with root.value. If you want to see the value of the left child of the root, you can see it with root.left.value. You can also see the left child of the left child dot left. And so on by adding more dot left, like that. The calculation method for gene coefficient to implement decision tree is as explained earlier. Oh, it's long. Okay, so it's long, but this allows us to build a decision tree. We actually using it. The flow is to first prepare the data, train the model, and then make prediction. Uh, if you want to change the data, you just need to rewrite this part, and it will work. The specific information about the iris dataset can be checked with iris.description. This dataset includes features such as sepal length, sepal width, like that. Sepal length, sepal width, petal length, petal width. The following is reference code. That's all. Okay. So, please work on the in-class report from the last page.